back in the quiet room, you and I. The lamp is still lit, just as we left it. The same warm circle of light on the table, the same gentle glow reaching into the corners. There's something comforting about returning to a space that hasn't changed, finding it exactly as you remember. The chair is still pulled close. The book is still open on the table between us. The air is still. It's good to be back here. In our first evening together, we noticed something strange. The universe, as we tried to add up its contents, didn't balance. The numbers refused to close. There were blank pages in the book where we expected text, and no matter how carefully we counted, the visible matter fell short. In our second evening, we sat with that strangeness and confirmed it. Galaxy rotation curves, gravitational lensing, the way clusters of galaxies hold together against their own motion. Multiple independent observations, each arrived at through different methods, all pointing to the same conclusion. Something is written on those pages. We just can't see the ink. The evidence is solid. The mystery is real. And tonight, we turn to a different question. Not what the evidence shows, but what the answer might be. Imagine we've stood up from the table and walked over to a shelf in the library. Not a distant room, just across a hall. The lamp's light reaches this far, soft and steady. On the shelf sit several volumes. Each one proposes a different answer to the question we've been holding. Each suggests what that invisible writing might say, what form the missing matter might take. Some of these books are thick and well-worn, with cracked spines and pages that fall open easily to familiar passages. Others are slimmer, with notes still penciled in the margins, ideas still being tested. None has been confirmed as the right answer, but none has been ruled out entirely either. We're not here tonight to pick a winner. That's not the kind of evening this is. We're here to understand what's on the shelf, to pick up each volume, look at it carefully, and set it back down, to see why each earned its place here, and what would need to happen for us to know which one is correct. Think of it as browsing, not deciding. There's a particular freedom in that, isn't there? When you browse a shelf without pressure, without needing to choose, you can let each book be what it is. You can appreciate the craftsmanship, the argument, the way ideas connect, without forcing a conclusion. You're not dismissing anything. You're not committing to anything. You're just looking, carefully and openly, at what's there. That's the spirit we'll hold tonight. The simplest framework goes like this. If something has mass but doesn't emit light or absorb it, if it interacts with gravity but barely touches anything else, then it's probably made of matter we haven't directly detected yet. New particles, in other words. Particles that exist outside the catalogue we've built so far. This is where the term dark matter becomes useful shorthand. Not darkness as mood or threat, but darkness as description. Matter that doesn't shine, matter that passes through telescopes without leaving a trace, that holds galaxies together through gravity alone. Most of the candidates we'll look at tonight fall into this category. Particles with different masses, different behaviors, different ways they might have formed in the early universe. Each one is a hypothesis built on mathematics, on observational constraints, on the way physics allows matter to behave. But before we walk along the shelf and pick up the first book, let's set one thing down clearly. These are not wild guesses. Each candidate emerged because it solved a problem, or fit a pattern, or appeared naturally in a larger theoretical framework. They're here because they're plausible, not because they're entertaining. Plausibility in physics is a narrow gate. The universe has rules. Any candidate has to pass through those rules without breaking them, and the rules are strict. So let's begin. Let's reach for the first volume, the one that's been studied longest, the one that for decades seemed most likely to hold the answer we need. The first book we pick up is thick, heavy in the hand. The spine is labeled WIMPs, weakly interacting massive particles. The name is precise, almost technical. These would be particles with mass, substantial mass, enough to account for the gravitational effects we observe in galaxies and clusters. And they would interact weakly, meaning they'd pass through ordinary matter almost without touching it. Not completely invisible to detection, but close. Very close. The weakly here refers to something specific. It's not a casual description. It refers to the weak nuclear force, one of the 4 fundamental forces in physics. The weak force is responsible for certain kinds of radioactive decay. It operates at extraordinarily short ranges, deep inside atomic nuclei, and it governs processes that allow particles to change type. If dark matter particles interact through the weak force, they'd behave somewhat like neutrinos. Neutrinos stream through the Earth by the trillions every second, barely noticing matter is there. They pass through you, through the chair, through the planet, without leaving a mark. WIMPs would do something similar, but they'd carry far more mass. Now here's the part that made WIMPs so compelling for so long. The part that made this book seem like it might hold the answer. The mathematics worked out almost perfectly. In the early universe, when everything was hot and dense, and particles were being created and destroyed constantly, there was a kind of equilibrium. Particles annihilated with their antiparticles, releasing energy, and that energy created new particle pairs, a continuous cycle. But as the universe expanded and cooled, this process slowed. Eventually, the universe became too sparse, too cool, for particles to find their annihilation partners easily. At that point, certain particles froze out. Their density stopped changing. What was left became a relic population, still present today. This is dense material, but the book explains it patiently. Let's stay with it a moment longer. Physicists can calculate how much of a given particle should remain after freeze-out. It depends on the particle's mass and how strongly it interacts. When researchers ran those calculations for particles interacting through the weak force, with masses in a certain range, roughly the mass of 100 protons, the predicted relic abundance matched the observed density of dark matter almost exactly. This wasn't proof, but it was striking, suggestive. It hinted that dark matter might not be exotic at all, might not require entirely new physics. It might be a natural consequence of forces and particles we were already studying for other reasons. Physicists called this coincidence the WIMP miracle. Not a literal miracle, but a mathematical one. A case where the numbers lined up in a way that felt almost too neat to be accidental. Let that sit for a moment. The elegance of it, the way separate pieces of physics, the weak force, the expansion of the universe, the observed density of dark matter, all seem to point toward the same answer. It's the kind of convergence that makes a hypothesis compelling. Not proof, but a kind of internal consistency that suggests you might be on the right track. So researchers built experiments, underground labs, careful detectors, years of patient observation. They set out to find these particles directly. Let's set this book down on the table for a moment and think about what it would take to detect a WIMP. What kind of room you'd need? What kind of listening? If WIMPs are real, they're passing through the earth constantly, through the walls, through the floor, through you and me as we sit here. Trillions of them, most likely, streaming from every direction, part of the dark matter halo that surrounds the Milky Way. Occasionally, very rarely, one should nudge an ordinary atomic nucleus. Just a gentle push, a transfer of momentum. The nucleus would recoil slightly, releasing a tiny pulse of energy. If you could detect that pulse, you'd have found a WIMP. The challenge is that the signal would be extraordinarily faint, fainter than almost any other signal you might want to measure. And the noise, from cosmic rays, from natural radioactivity in the surrounding rock, from stray particles of any kind, would drown it out completely. So the experiments went underground, deep underground, into old mines and tunnels, where kilometers of rock overhead filter out most of the cosmic rays. These are quiet rooms, still and patient, not dramatic spaces, not eerie, just carefully shielded chambers where detectors can sit in stillness, waiting for something real to appear against a nearly silent background. Think about what it means to build a room like that, to go deep into the earth, to shield everything, to cool the detectors to near absolute zero, and then to wait. Years of waiting sometimes, watching for a single flash of light, a single pulse of energy that might be the signal you're looking for. The patience required is extraordinary, not just from the instruments, but from the researchers. To design an experiment that might run for a decade, to check and recheck every possible source of background noise, to sit with the possibility that the signal might never come, and still keep the detector running, still keep recording data, still keep searching. One of the most sensitive is called Lux Zeppelin, or LZ for short. It sits in the Sanford Underground Research Facility in South Dakota, about 1.5 kilometers below the surface. The detector holds 7 tons of liquid xenon, cooled and purified until it's extraordinarily clean, with almost no contamination from natural radioactivity. When a particle interacts with a xenon nucleus, it produces 2 signals, a flash of light and a pulse of ionization. By comparing these 2 signals, researchers can tell what kind of particle caused the interaction. Background radiation leaves one pattern. A WIMP, if it appeared, would leave another. LZ has been running for over 400 live days now, watching, recording, and it's found nothing that can't be explained by known particles. No excess, no signal that points to WIMPs. What it has done is set extraordinarily tight limits. If WIMPs exist in certain mass ranges with certain interaction strengths, LZ should have seen them. It hasn't, so those possibilities are ruled out. There's another detector called XENONNT, running in Gran Sasso National Laboratory in Italy. It reached a milestone recently, a kind of threshold physicists both hoped for and dreaded. It detected recoils from solar neutrinos, not dark matter, just ordinary neutrinos from the sun. interacting with the xenon at such low energies that the signal is almost impossible to distinguish from what a WIMP might produce. This is sometimes called the neutrino fog. It means the instrument has become almost too sensitive. Any further improvement will require new techniques, new ways of filtering out the neutrino background to see if there's anything else underneath. Back here by the lamp, we can appreciate what this means. These experiments are pushing the limits of what's possible to measure. They're detecting signals so faint that they're brushing up against fundamental limits. Not limits of technology, but limits set by the universe itself. Let's rest here for a moment, because it's easy to hear no detection after decades of searching and think the search has stalled, that nothing is being learned. But that's not how it works. Every null result teaches us something. It rules out part of the possibility space. If WIMPs exist with this mass and this interaction strength, we should have seen them. We haven't. So they don't exist there. The window narrows. Think of it like testing what the frame of the house is made of. You test for wood, not wood. You test for steel, not steel. Each test teaches you something, even when the answer is no. Even when you haven't found the right material yet. You're narrowing the possibilities, learning what the frame isn't, getting closer to what it might be. This is progress, real progress. It forces theorists to refine their models, to abandon certain parameter ranges, to look elsewhere. It shapes the next generation of experiments, tells them where to search, what sensitivity they'll need to reach. The WIMP hypothesis is not dead, but it's been constrained, bounded, pushed into corners of the parameter space that are harder to reach. If WIMPs exist, they're either lighter than expected or heavier, or they interact even more weakly than the original models suggested. The window is smaller than it used to be, but it's still open. And in the meantime, the experiments continue. New detectors are being built with better sensitivity, different target materials, new techniques for filtering out background noise. The search hasn't stopped. It's adapted. But let's not stay in this one place too long. Let's turn away from the underground labs and look at another volume on the shelf. A different candidate entirely. One that's lighter, stranger, and in some ways more elusive than WIMPs. The second book we pick up feels different. Lighter in the hand, slimmer, but with a kind of elegance to it. The pages are clean, the margins filled with careful annotations. The spine reads, Axions. These are not massive particles. They're extraordinarily light. If a WIMP might weigh roughly as much as 100 protons, an axion might weigh 1/1000th of that. Or less. Perhaps much less. And yet, if they exist in vast enough numbers, swarms of them, filling space like a fog, they could still account for all the dark matter we observe. Axions weren't invented to solve the dark matter problem. They emerged from something else entirely, a different puzzle buried inside particle physics. Physicists Roberto Pecci and Helen Quinn proposed them in 1977 as a solution to what's called the strong CP problem. The details involve symmetries in the equations that govern the strong nuclear force, the force that holds atomic nuclei together. We don't need to follow that thread tonight. It can rest on the shelf. What matters is that axions appeared naturally as part of the solution. And once theorists realized axions could exist, someone noticed something interesting. If axions were produced in huge quantities in the early universe, they could have the right properties to be dark matter. Not by design, by accident. The axion became a candidate, not because anyone set out to explain dark matter, but because the mathematics led there on its own. Think about what that means. Imagine opening a book expecting one story. A story about nuclear forces, about symmetries in equations, and finding that same book also speaks to an entirely different question you'd been wondering about. A question about the missing mass in galaxies, about the invisible scaffolding holding the universe together. The book wasn't written with that question in mind, but it answers it anyway, or might. There's something deeply appealing about that. A kind of coherence to the universe that you don't expect, but recognize when you see it. It suggests that different pieces of physics might connect in ways we don't initially understand, that solving one puzzle might accidentally illuminate another. But appealing isn't the same as confirmed. The book is elegant, yes, but we don't know yet if it's the right book. Back here by the lamp, we can set this volume down gently and think about what it would take to know. How you'd look for an axion, what kind of signal it would leave, what kind of room you'd need to build. Axions, if they exist, wouldn't interact through the weak force. They'd barely interact with anything, but they would have one faint coupling to electromagnetic fields. This means that in the presence of a strong magnetic field, an axion could occasionally convert into a photon, a particle of light. The conversion rate would be incredibly low, and the photon would be extraordinarily faint, but it would have a very specific frequency, determined by the axion's mass. If you knew where to look, you could tune a detector to that frequency, like tuning a radio to a particular station, listening for a signal that shouldn't be there. Imagine sitting in a quiet room with an old radio, the kind with a dial you turn slowly, manually, listening to the hiss of static as you move through the frequencies. Most stations are silent, empty channels, but occasionally, if you're patient, if you turn the dial carefully enough, a voice emerges from the noise. Faint at first, then clearer. That's the image here. You're sitting in silence, turning the dial slowly, listening for something you're not sure exists. The vast majority of frequencies are empty, just static, just noise. But if the signal is there, if you pass over it, you'll hear it. The patience required is extraordinary. You can't rush through the dial. You have to spend time at each frequency, long enough to be sure that if there's a signal, you'd detect it. And the frequency range is enormous. Thousands upon thousands of stations to check, one by one. This is what axion experiments do. They're not underground labs looking for nuclear recoils. They're cavities, metal chambers filled with powerful magnetic fields, cooled to near absolute zero, listening for faint radio signals emerging from the quantum vacuum. One of the leading experiments is called ADMX, which stands for Axion Dark Matter Experiment. It's located at the University of Washington in Seattle. Over the past several years, ADMX has scanned a frequency range corresponding to axion masses between about 3.3 and 5.4 microelectron volts. It's reached what's called QCD axion sensitivity, meaning it's sensitive enough to detect the type of axion that solves the original strong CP problem, if it exists in that mass range. So far, no signal. But the search continues. ADMX is expanding its range, scanning lower and higher frequencies, one narrow band at a time. There are other experiments too. IAXO, which will search for axions produced in the Sun. CASPER, which uses nuclear magnetic resonance techniques to detect axion-induced oscillations. ABRACADABRA, which listens for extremely light axions with a different detection method entirely. Each experiment covers a different part of the parameter space. Each one requires extraordinary precision, careful shielding from electromagnetic noise, patience as the detector tunes slowly through the vast range of possible axion masses. Let that diversity sit for a moment. These aren't all the same experiment repeated. They're different approaches, different techniques, different windows into the same question. Some look for axions passing through the detector. Some look for axions produced in the Sun. Some scan high frequencies, some scan low. Together, they're covering the possibility space systematically, carefully, leaving fewer and fewer places for the signal to hide. It's slow work. The frequency range is enormous, and you can't rush through it. You have to spend time at each frequency, long enough to be confident that if there's a signal, you'd see it. Back by the lamp, we can set this down gently. The axion search is ongoing. The methods are advancing, but the answer hasn't come yet. There's something worth noticing about the current moment in dark matter research. Something that's shifted over the past decade or so. For a long time, WIMPs were the default hypothesis, the leading candidate. When physicists talked about dark matter detection, they usually meant WIMP detection. Axions were secondary, interesting, worth pursuing, but not the main focus. That's changed. Today, axions and WIMPs sit on roughly equal footing. Both are leading candidates. Both command significant experimental effort, funding, attention. If you ask a researcher which one they think is more likely, you'll get different answers depending on who you ask. Two things drove this shift. First, the silence from WIMP searches. Decades of increasingly sensitive experiments, all returning null results, pushed physicists to take alternatives more seriously. Not because WIMPs are ruled out, but because the simplest versions of the WIMP hypothesis, the ones that seemed most natural, haven't appeared where we expected them. Second, technological advances. Axion detection requires extraordinary sensitivity to electromagnetic signals. It requires quantum sensors, superconducting cavities, techniques that filter out noise at levels that were barely possible 20 years ago. And those technologies have matured. The instruments that once existed only as proposals, as sketches in research papers, have been built. They're running. What was theoretical is now practical. What was at the edge of feasibility is now routine, or close to it. The tools have finally caught up to the question. So we're in a kind of golden age of axion searches. Multiple experiments, different techniques, scanning different mass ranges, all running in parallel. The parameter space is vast, but it's being covered systematically, carefully, step by step. And yet, as with WIMPs, no confirmed detection. The search continues. Large regions of parameter space remain to be scanned. The answer might be there, waiting. Or it might not. We don't know yet. So we keep both books on the shelf, and we let the experiments continue. Let's turn the page now. Let's look at what else is there, further along the shelf, where the volumes get slimmer and the ideas more speculative. There's another book here, a bit older, with a dog-eared cover and annotations throughout. Most of its chapters have been checked, tested, and set aside, but not all. The spine reads, Primordial Black Holes. This is a different kind of candidate entirely. Not a new particle, not an extension of the standard model, just black holes. Tiny black holes, formed not from collapsing stars, but from density fluctuations in the first fraction of a second after the Big Bang. The idea is old, dating back to the 1970s. If the early universe had regions that were slightly denser than average, and if those regions were small enough and dense enough, they could have collapsed directly into black holes before the universe had time to smooth them out. These wouldn't be stellar black holes, massive remnants of dead stars. They'd be small, perhaps very small, and if enough of them formed, they could account for the dark matter we observe. No new physics required, just gravity doing what gravity does. It's an elegant idea in some ways, but observations have constrained it heavily. Multiple lines of evidence have ruled out most of the possible mass ranges. If primordial black holes were too light, they would have evaporated by now through Hawking radiation. If they were too heavy, we'd see them through gravitational lensing. When a black hole passes in front of a distant star, its gravity bends the star's light, causing a brief brightening. Surveys have looked for these micro-lensing events and found far fewer than you'd expect if primordial black holes were abundant. The cosmic microwave background also constrains them. If there were too many small black holes in the early universe, they would have affected the formation of the first atoms, leaving a signature in the CMB that we don't observe. And more recently, gravitational wave detectors like LIGO have ruled out certain mass ranges. If there were many black holes with masses between about 10 and 100 times the Sun, they'd be merging frequently enough that we'd see more gravitational wave signals than we do. So most of the parameter space has been checked. Most chapters in this book have been closed, but not all. A narrow window remains. Black holes with masses roughly equivalent to asteroids, between about 10 to the 17th and 10 to the 22nd grams. These would weigh as much as a mountain or a small asteroid, but they'd be tiny in size, roughly the size of a single atom. They're not the favored candidate. Most physicists would bet on WIMPs or axions before primordial black holes. But this mass range hasn't been definitively ruled out, so the idea stays on the shelf, an older book with most pages turned, but a few chapters still unread. And then there are the margin notes, ideas that are more speculative, less developed, but still written down because they're not impossible. Sterile neutrinos, for instance. We know that ordinary neutrinos exist, 3 types of them, part of the standard model. But several experiments over the years have reported anomalies, small excesses or deficits that don't quite fit the 3-flavor picture. One way to explain these anomalies is to add a 4th type, a sterile neutrino, meaning it wouldn't interact through the weak force at all, only through gravity and possibly through very faint mixing with ordinary neutrinos. If sterile neutrinos exist, and if they have the right mass, they could contribute to dark matter. Not all of it, perhaps, but some. The hints aren't conclusive. Different experiments see different things. So this remains a note in the margin, plausible but not confirmed. Or self-interacting dark matter, SIDM. Most models assume dark matter particles pass through each other as easily as they pass through ordinary matter. But what if they don't? What if dark matter has its own interactions, its own internal forces? This could explain certain small-scale puzzles in galaxy structure, cores that appear flatter than simulations predict, for instance. The idea is testable. If self-interactions exist, they should leave signatures in how dark matter distributes itself on small scales. But the evidence so far is ambiguous. So it's another margin note, worth writing down, worth checking, not yet part of the main text. And then there's the dark sector. Not a single particle, but a whole hidden family of them. A parallel set of matter and forces, interacting with each other, but only very weakly with the matter we know. Imagine it like this. Ordinary matter is governed by forces, electromagnetism, the strong and weak nuclear forces. Those forces allow ordinary matter to interact with itself, to form structures, to emit light. What if dark matter has its own forces, its own version of electromagnetism perhaps, its own interactions? This would allow dark matter to have rich internal dynamics, its own structures, even its own analogue of chemistry. It's speculative, but it's motivated by a simple observation. If dark matter is 85% of the matter in the universe, why should it be simpler than the matter we see? Why shouldn't it have its own complexity? The challenge is detection. A dark sector would be extraordinarily difficult to observe. You'd have to catch one of those rare moments when it couples faintly to ordinary matter, through gravity or through extremely weak mixing with known particles. A few experiments are looking for such signals, nothing confirmed yet. But the idea remains in the margins, because it's not implausible. These are not the leading candidates. They're possibilities, sketches, ideas that might connect to something real or might dissolve under closer scrutiny. But they're part of the picture, part of what's being explored. Let's step back from the shelf for a moment. Back to the chair, the table, the steady light. We've looked at several candidates now. WIMPs, axions, primordial black holes, and a handful of more speculative ideas. Each has its own logic, its own experimental program, its own way of fitting into the larger structure of physics. And here's something worth appreciating. The shelf is full. That's not a problem, it's a feature. Science doesn't require that we have only one hypothesis at a time. It works by exploring multiple possibilities in parallel, testing each one against the evidence, letting the data narrow the field. Some ideas will be ruled out, some will survive. One, perhaps, will turn out to be correct, but we don't know which one yet. And that's fine. The process is working as it should. Researchers are searching, carefully and systematically, across a wide range of possibilities. Each null result teaches something. Each new technique opens a part of the parameter space that was previously inaccessible. The search is broad, the search is patient, and the search continues. Let's turn to something else now. Not the candidates themselves, but the nature of searching. What it means to look for something this elusive, and why silence, decades of silence, doesn't mean the search has stalled. We've said this before, but it's worth lingering on, worth really settling into, because the instinct to hear no detection and think nothing learned runs deep. But exclusion is progress. Every time an experiment runs and finds nothing, it's not starting from zero the next time. It's narrowed the field. It's ruled out possibilities. If dark matter interacts in this way, with this strength, in this mass range, we should have seen it. We haven't. so it's not there. Think of it through the house metaphor. You're trying to determine what the frame is made of. You test for wood, not wood. You test for steel, not steel. You test for aluminum, for copper, for various composites. Each test that comes back negative isn't a dead end. It's information. You're learning what the frame isn't. You're narrowing the search space, getting closer to the materials that remain possible. In dark matter searches, this process has been ongoing for decades. Each generation of experiments has pushed the sensitivity deeper, covered more parameter space, tested more hypotheses, and each null result has shaped the next generation, told them where to look, what techniques to develop, what backgrounds to worry about. Lux Zeppelin didn't just fail to find WIMPs. It ruled out huge swathes of the WIMP parameter space with unprecedented precision. ADMX didn't just miss axions. It covered specific frequency ranges with sensitivity high enough to detect the theoretically motivated versions of the particle. And it found they're not there. Not in those ranges, at least. This is how science refines itself. Not through sudden revelations always, but through patient accumulation of constraints. The picture gets sharper even when the answer hasn't arrived yet. And there's something else. Something maybe harder to articulate, but worth trying. When you've ruled out the simplest possibilities, when the easy answers haven't appeared, it means that whatever the truth is, it's more subtle than you expected, more interesting perhaps. Reality is under no obligation to be simple, and when it refuses to be simple, when it hides in corners of the parameter space you didn't initially think to look, that's not failure. That's the universe teaching you something about how it works. Let's think about timelines for a moment, about how long discoveries can take, and what that means for where we are now. The neutrino is a good place to start. Wolfgang Pauli proposed its existence in 1930 to explain certain properties of radioactive decay. The numbers didn't balance without it. Energy seemed to disappear. So Pauli suggested an invisible, nearly massless particle that carried the missing energy away. It made sense mathematically, but detecting it seemed almost impossible. Neutrinos barely interact with matter. They pass through everything. How do you catch something like that? It took 26 years. Clyde Cowan and Frederick Rhines finally detected neutrinos in 1956, using a nuclear reactor as a source and enormous tanks of water as a detector. 26 years from hypothesis to confirmation. Or consider the Higgs boson, predicted in 1964 by multiple theorists, working independently as the mechanism that gives particles mass. The mathematics fit beautifully into the standard model. It explained why certain particles have the masses they do, but detecting it required energies far beyond what any particle accelerator could reach at the time. It took 48 years. The Large Hadron Collider finally found the Higgs in 2012, after decades of technological development, billions of dollars in funding, and the coordinated effort of thousands of physicists. 48 years from prediction to discovery. Or gravitational waves. Einstein predicted them in 1916 as a consequence of general relativity. Ripples in space-time itself, traveling at the speed of light, produced by the acceleration of massive objects. The equations were clear, but the effect seemed impossibly faint. Einstein himself doubted they could ever be measured. It took 99 years. LIGO detected gravitational waves in 2015 from the merger of two black holes more than 1 billion light years away. 99 years from prediction to confirmation. Let that number sit for a moment. Nearly a century. Generations of physicists working on a problem, building detectors that got closer and closer to the required sensitivity, until finally the instruments were good enough and the signal appeared. Back here by the lamp, we can hold that patiently. 99 years isn't a shortcoming. It's the time the universe needed to reveal itself. The time it took for the question to mature, for the technology to catch up, for the right experiment to be built in the right way. The pattern here isn't that science is slow. It's that the universe doesn't work on our schedule. Some questions take time to answer, not because we're not trying, but because the technology has to catch up to the question. Because the signal is so faint that you need extraordinary precision. Because the right experiment hasn't been built yet, or the right theoretical framework hasn't been developed. But here's the thing. The universe doesn't hide forever. If something is real, if it's there, patient effort eventually finds it. Not always quickly, not always when we'd like, but eventually. Dark matter might take longer still, or it might be detected tomorrow. We don't know, but the search continues, and the methods improve, and the sensitivity deepens, and that's all we can do. Stay patient, keep looking, let the experiments run. So what's ahead? What's on the horizon in terms of experiments and techniques? Lux Zeppelin is still running. It's aiming for 1,000 live days by 2028, which will push its sensitivity even further into the parameter space. If WIMPs are there, in the ranges it's searching, LZ will likely see them. ADMX is continuing to scan new frequency ranges, expanding both upward and downward in axion mass. Each scan takes time, but the coverage is systematic. The parameter space is being explored carefully, methodically, and there's something else. A consortium called XLZD, short for Xenon LZ Darwin. 3 major collaborations, previously building separate detectors, have merged their efforts. They're planning the next generation. A detector with 100 tons of liquid xenon, 10 times larger than anything built so far. If it's funded and constructed, it will push deep into the neutrino fog, searching for signals beneath the background of solar neutrinos. Back by the lamp, these numbers are just marks on a page. What they represent is patience scaled up. Larger detectors, longer observation times, deeper sensitivity. The search continuing, step by careful step. This isn't hype. It's not a promise of imminent discovery. It's just the continuation of the search, with better tools, deeper sensitivity, more systematic coverage of the possibility space. The search continues. That's the phrase to hold here. Not with urgency, not with desperation, just with patience and care. The experiments are running, the data is accumulating. The field is narrowing step by step, and if the answer is there, we'll find it. In time. Let's set this section down gently and turn toward the end of the evening. Back to the table, the book, the quiet room where we started. We've come a long way tonight, you and I. Let's bring the evening to a close by retracing the thread, seeing what we've held. Tonight we looked at the candidates, the possibilities for what dark matter might be. We walked along the shelf, picked up each volume, looked at it carefully. WIMPs, Massive particles interacting through the weak force, with a beautiful mathematical coincidence that made them seem natural. Decades of underground searches, extraordinary sensitivity, and so far, silence. The window is narrower than it was, but still open. Axions, extraordinarily light particles proposed to solve a different problem entirely, now standing as a co-leading candidate. Radio cavities, quantum sensors, a golden age of axion searches, and still no confirmed signal. But the parameter space is vast, and the scanning continues. Primordial black holes, an older idea, mostly constrained, but with a narrow window still open. Tiny black holes formed in the first moments after the Big Bang, weighing as much as asteroids but no larger than atoms. And the margin notes. Sterile neutrinos, self-interacting dark matter, the dark sector. More speculative, less developed, but still on the page, because they're not impossible. None confirmed, none fully ruled out. The shelf holds multiple books, and the chapter is still being written. This is not a story with a resolution yet, but it's a story worth following, because the answer, when it comes, will reshape our understanding of the universe at the most fundamental level. Let's pull back for just a moment and trace the thread through the season so far. In our first evening together, we noticed something strange. The universe, when we tried to add up its contents, didn't balance. There were blank pages in the book, pages where we expected text, but saw only emptiness. In our second evening, we sat with that strangeness and confirmed it. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the way clusters of galaxies hold together, multiple independent lines of evidence, each arrived at through different methods, all pointing to the same conclusion. Something is written on those pages. We just can't see the ink. Tonight, we looked at the candidates for what that writing might say. Particles with different masses, different interactions, different ways of revealing themselves. Each one plausible, each one testable, none confirmed yet. And next time, our next evening together, we'll turn to the other piece of the puzzle, the even larger piece. Not the missing 27%, but the missing 68%. Not dark matter, but something stranger still. Something that doesn't cluster in galaxies, doesn't bend light, doesn't pull things together. Something that seems to be pushing the universe apart. But that's for another evening, another conversation, another time when we sit down together, with the lamp lit and the book open between us. For now, let's just rest here. Let's let the questions settle. The book is still open on the table, but we can leave it there. The shelf is still full of volumes, each one holding a different possibility. And that's all right. We don't need to take one down and declare it the answer. We can let them sit there, side by side, waiting for the experiments to tell us which is correct. The lamp is still steady. Its light hasn't changed. The room is still quiet, still patient. Outside this room, the search continues. Detectors are running. Data is accumulating. Researchers are testing hypotheses with care and precision. But in here, we can rest. We can let the complexity be complex. We can hold the uncertainty without needing to resolve it tonight. Science doesn't rush toward a finish line. It's a process of narrowing uncertainty, of ruling things out, of discovering what the universe is made of, one careful step at a time. And that process doesn't require urgency from us. It doesn't ask us to force conclusions. It asks us to be patient, to stay curious, to trust that the truth will emerge when the evidence is ready to show it. We don't know which book on the shelf holds the right answer yet. Maybe it's WIMPs, maybe it's axions, maybe it's something we haven't thought of, something that will only become clear when a new piece of evidence appears, when a new theoretical framework develops, when someone notices a pattern that's been sitting there all along, but no one quite saw. And that's fine. The universe has been here for 13.8 billion years. It's been holding these secrets for all that time. It can hold them a little longer while we work to understand them. The book will be here when we return. The lamp will still be lit. The questions will still be waiting, patient and open, ready for us to sit with them again. For tonight, that's enough. Rest easy. The search continues, but you don't have to carry it. Just know that it's happening. Know that the experiments are running, that progress is being made, that the field is narrowing step by step. And when there's something new to share, we'll open the book again together. Until then, let the room be still. Let the pages rest. Let the universe keep its mysteries just a little longer. We'll be ready when the answer comes.